Okay. So what I was thinking is I would work today through basically practice 5. So I picked out a few problems that I think are useful. So it's basically the equivalent of Connect 5 or C5 as I call it in the thing. And so basically today I was thinking I would work through moments and couples. I really just dislike couples. I just don't really understand why we think in those terms, but whatever. So I don't really ever remember thinking about couples outside of statics class, but for completeness, we will stay with that. So anyway, so I figured I would work through some of these, and if any of you guys, had one in specific, like with the moment that you were like, this really confuses me, we can totally work that. But I have some picked out that I can work. Or if some of you guys are like, you know what, I don't want to watch Dr. Wagner work problems. I want to work I'd feel better just kind of being on my own. Just let me know, and I can set up like if you want to go off to the side and work something, or if you want to like pair up with somebody and just go into a waiting room or something, what do they call that, like a side room, and work it, then that would be fine too. Like if you're like, I want to work with so and so, and we're going to work on the homework, and then we're going to jump back in because we get stuck, that's fine too. But I figured, right now we'll kind of jump back a week or two, and we'll work moments, since moments are kind of confusing. And then next class we'll do reactions, and then the following class we'll do trusses. Trusses will cover moments and reactions. So next week we'll do trusses both on Monday and Wednesday. Any questions, thoughts? Most of you guys are muted right now, which is of course totally fine.
That works for me.
Okay, thanks, Parker. Just it also reminds me that you guys can hear me. So all right, so let's so what I'm going to do, so I'm going to start with on the practice.
So I just have a question before you start, sir.
Sure.
Yes. Now, so for the videos we watch on YouTube, we're gonna start from video number 37, or we need to go back a few videos. I mean, for the next test or for the next section.
Oh, well, the next test will cover from, I guess, where did we stop? We didn't do.
We stopped, I think, in 30. It was the last review for the test 1.
Right. So the next test will start. The next test will start wherever the last one, stopped. I don't remember.
Okay.
I don't know what
I got it.
lecture that was, but we didn't do moments.
It was like 31.
So we didn't do moments. So yeah. So anyway, so if you have Connect, if you wanted to open that to see kind of the problem, I tried to make it so that maybe I can share both screens that I'm working on. I don't know if I can do that. But I was going to go to problem number, wait, where's my list? Oh no, I didn't lose my list. Okay, so I was going to go from the practice set. I was going to do number 7. So some of these will overlap with the ones that we're doing, and or the ones that actually got assigned. So I was going to start with number 7, so 7 through 9 of 19, and let me see if I can get I want to share the whiteboard. Share screen. I've stopped. Okay, fine. Where's the whiteboard? Oh, here's the whiteboard. All right. So if you don't have it open, it's okay. I'm gonna draw a real quick schematic of what's going on there. And so let's see. Oh, we're in yellow. Yellow is not a very good color. Can you give me a different color? Sorry, I'm learning how to use this. Come on. Where's the whiteboard settings? Oh, here we go. Okay, sorry. Can we get a different color? Okay, we go black. Okay, so all right. So this is what the problem looks like. It looks something like this, and they've got a something that's in here. Okay, and it's framed like this. Okay, and they give you points. This is A, B, C, D, and at C they've got a force going this way. At B they've got a force going this way, and at A they've got a force which they call P, and each of these is 150. Come on, you can do it. Okay, there you go. So each of these is 150 apart. Okay, so this is 150 millimeters. Okay, so each of those 150 millimeters apart. And this force right here, these two are both, this one's 600 newtons and this one's 400 newtons. And this one is, they call it P, but I'm not going to bother with P because for mine it says P is 220 newtons. Okay, now what it wants to know is, okay, so the A part, which will work right now, is it says find the resultant of these forces, and distance from ground, Okay, and this is a weird question because you wouldn't normally, like, I don't know, you wouldn't really find a resultant, or I don't know if resultant is the right word, but normally you wouldn't do this, right? So we're adding forces, they don't line up. But sometimes what you want to do is you want to come up with an equivalent system that basically, works exactly the same way, but you just want a single force, okay? And this doesn't, in statics, you don't normally want to do this. So basically we're going to come up with one force and we want to know where does it act, okay? And we need to know, and it's going to basically have essentially the same effect on this beam as what we've got. So we want to know what's the magnitude of this thing and where does it act. And in statics, this is pretty rare that you would want to do this because the effect on the internal effect on the beam will be different. But like, for example, I teach fluid mechanics, and in fluid mechanics, it's pretty often that I don't want to think about the fluid itself anymore. I just want to think about the net effect of all that fluid on like a levee. So if you can imagine you had a levee, right? And you've got all this water, backed up against the levee, you might say, well, the pressure on this levee is greatest at the bottom of the levee, but I don't want to think about all that, right? I just want to think about a single force. I want to replace all this pressure with a single force that helps me figure out, like, is my levee strong enough? And so that's just something you might want to do sometimes. And there are lots of times you might want to do that in fluids. In statics, it's pretty rare, but this is just kind of a skill to set you up for what's going on next. So what we're going to do is we're going to basically look for an equivalent system. And what I'm going to do is I'm going to think about it, take all of these forces, and I'm going to think about the effect of all of these forces, basically at the bottom. So what I know is I want to say, well, the sum of these forces in the x direction equals something, right? And I want that to be the same down here. Okay, so I want it to be the same. So in the x direction, this is actually pretty straightforward because we're just going to say, well, we've got 220 to the right. Okay, I've got 600 to the left and 400 to the left. Okay, so that's the net effect of this force. And so that's 1,000, 200 minus 1,000, so that's negative 800. Okay, so that means down here, whatever my force is, it's going to be negative 800 newtons. Okay, good morning, Rye. So there you go. So that's the first thing we want. So our resultant over here is going to be 800 newtons to the left. Okay, now the next thing we want to do is this force needs to basically have the same effect, the same like moments. Okay, so I can kind of say, what is the sum of the moments here? And I have to pick a point that I want to match the moments on. And it really could be anywhere. Like I could do this moment around the point A, I could do it around the point B, I could do it around the point C or point D, or I could even do it around a point way out in space if I wanted to. That seems a little silly. I usually like to choose the base. And so we do that. One thing to consider before I do this, this is a little bit unrelated on this problem, is that this is about the point D, but I want to make the point that this is in the Z direction, Z about the point D. Okay, and that's something that a lot of students, certainly in 2D, you don't even have to think about. But when you get to 3D, it becomes paramount that you consider this. And so usually in statics, this is my X direction. Okay, and we use a right-handed coordinate system. And so to do that, this is my fingers. Okay, this is the Y direction. Okay, it doesn't have to be in this direction, but usually we like Y to be up, usually. And so that is the palm of my hand. Okay, and that means that the thumb, okay, is coming straight out at you. Okay, so the thumb is going towards your face, towards face. Okay, and your fingers, like when they curl, like if you put your fingers like this, your fingers will curl this way. Okay, and that tells you which way is positive. Okay, which way your fingers curl is the positive direction. Okay, and it is the Z direction because your thumb is, because it's basically going around this Z axis. Okay, now we don't normally think about that in 2D, but in 3D it's necessary to consider that. So the 2D is kind of the easier case. Anyway, so everything that is going to go in the same direction as these fingers curl, we're going to call that positive, and everything that would cause this thing to spin around this point D will be negative. So hopefully you can see that you know, this 400 Newton and the 600 Newton are going to cause this thing to spin positive because they're going to go in the same direction as your fingers curling, and this 220 will be negative because it's going to cause things to go in the opposite direction as your fingers curling. Okay. So, I mean, and that's kind of the most important thing we want to learn out of this particular question. So the moments here, we've got, let's see, we've got 600. Well, I've started at a random spot, but 600 Newtons, and that's going to create a positive moment, and its perpendicular distance is from here to here. Okay, so that's going to be 300 millimeters, so 0.3 meters. Okay, this 400 will also be positive, so I'm going to put a little positive sign there, and we'll do the 400 Newtons. Okay, times, now its distance from D up, I guess this is kind of a poor drawing, but that's 150 millimeters, so 0.150 meters. Okay, and then we've got this 220, which is going the opposite way, so that'll be minus 220 Newtons. Okay, and its perpendicular distance is 450, so 0.450 meters. Okay, so we could add all that up. Sum of the moments in the Z direction around point D. Okay, and I'll just use a calculator real quick. 600 times 0.3 plus 400 times 0.15 minus 220 times 0.450 equals, so this is 141, and that's newtons times meters. Okay, so that's the net effect of all three of these at D. Okay, it's basically if I wanted the equivalent force and couple at the bottom, I could easily write an equivalent system like this if I wanted to. Okay, and I could say, oh, well, it's equivalent to having a force going this way at 800 newtons and a moment of 141 newtons per meter. That's positive, so that's going to go that way, 141 newtons times meters. But the question was, it wanted one force and the distance from the ground. So basically, we need to move this thing back up somewhere, this force back up somewhere, such that there's no moment. Okay, and so that's a little bit annoying. So basically, we're going to look over here to this drawing. And this moment, this 141 newtons times meters, okay, it has to basically be taken up in this distance, essentially. So basically, what I'm going to say is, I'm going to say, okay, well, I need this moment of 141. I know the moment, so that's going to be a force. So this resultant times a perpendicular distance. And so the moment I know is 141 newtons times meters. And this resultant is 800 newtons. And this will tell me the perpendicular distance that this thing needs to act in order to give this moment. Hopefully that's making sense. So if I do D perpendicular, I can just divide 141 by 800. Okay, so that's just the algebra. And notice that based on units, these newtons will cancel and I'll be left with meters. So I'll get 0.17625 meters, or probably, since I want you to report 3 significant digits, I can't get my pen down there. So let's just do it up here. Oh, come on. Yeah, I know. Get out of here. Go away. Sorry, I got a stupid. Okay, yep, I know. I don't want this. Thank you. Kidding me? Go away. That's fine. Can you just, oh, hold on. Okay, good. Okay, yeah, so I'll just, okay, here we go. Okay, there you go. Okay, so yeah, so D equals, since I want 3 sig figs, we'll say 176 millimeters. Okay, and that would be the answer that you would get. Yeah, so that's how we do it. Oh, did I do something wrong here? I did do something wrong here. Oh yeah, I solved. Sorry, this number right here should have been 220, which would have made this. I guess this would have made it negative 780. Anyway, that would have percolated all the way through, and we've gotten a slightly different number. So I apologize for that. So, but I mean the method is correct. Okay, so basically we could have said, so this is an equivalent force couple. This is like an equivalent force moment system, and this is an equivalent system also. Okay, but instead of, but this distance would be 176 millimeters. Okay, either one is equivalent. So this is obviously in a lot of ways the simplest. So this is, the way a lot of times you would want to be able to write this. Okay, so that's that idea.
I just have a question, sir.
Go ahead.
Oh, let the lady go first. I'm sorry.
Okay, no problem.
You can go ahead. It's fine.
You all are so polite. Somebody speak.
I was just curious. So we get negative 800 for the sum of f of x, or f in the x direction. Is that just to give us sort of the direction of the resultant forces, and that's not carried through the rest of the problem?
Oh, you mean like for the moment?
Yeah.
Okay, yeah. So there's two ways to calculate moments, and this is a great question, and I'm gonna cover this in a second. Is, as far as I'm concerned, there's two ways to calculate a moment, and I don't want to erase this because we've got another question coming. But so the way I look at it is there's two ways, and one of them is to do this R cross F, right? And what I do here is I insert the signs, okay, carefully. And what will happen is it will export the correct answer, okay? I'm getting really low and it doesn't like when I go down there. So export the answer with the correct signs. Okay, so this is one way to do it, okay? And, that involves finding a cross product. On a simple problem like this, doing those cross products is, it's kind of overkill. The other way to do it, excuse me, not some of the moments, we'll just say for a moment. So any moment you could calculate that way, okay? And the other nice thing about this is it will calculate it for you in 3 dimensions. So there's a lot of times when this is a really good way to do it. The other way to do it, and this is the way that I prefer, actually I prefer you know how to do both, is you do moment equals force times the perpendicular distance. And in that case, I always plug in positive values and I think about the sign. Okay, so basically I plug in positive values and then I say, okay, is this causing a positive moment or a negative moment? And this one is easier to solve, but you have to think, but the key is you have to be able to think about which way these things go. So you have to be able to think clockwise or counterclockwise, generally speaking. Does that make any sense? I mean, I'll show you one in a more difficult one. I'll do both of these to kind of show you what I mean by that. But on this one, the perpendicular distances were easy to see, because they were kind of given. And so this will save you a lot of time if you can do this instead of this.
Okay.
So to me, it's best to be able to do both. And as you move through your engineering education, most of the time you're going to do this. So yeah. So basically, I like to think about the signs for the moments by doing it this way. Does that answer your question, Parker?
It does.
Okay. Mohammed, what was your question?
Yes. When you find the moment Z to D, you have 0.3. Where did you get that from? I just didn't get
Oh, this one right here?
Yes.
Okay, so what I wanted was, so that was for the 600 Newton force. and I wanted to know how far away from D did it act. So D is right here. Well, it's been smooshed away. Okay, and so I wanted to go, so the distance that is away is 150 plus 150. So that's 300 millimeters. And 300 millimeters converts to 0.3 meters.
Okay. I got it. Thank you so
Okay.
much.
Okay. Anybody else? Oh, Rye, just in answer to the chat, Rye, this lecture will be posted. I hope so. I hit record. Hopefully it's recording. I've never successfully recorded a Zoom. I didn't worry about my other Zoom lectures because they were just office hours. I've never done a Zoom lecture, so hopefully this is fairly clear. I'm looking at it on the other screen. It sure looks like a mess. I'm used to obviously teaching in a classroom where you have way more whiteboards. Okay, so I'm going to move on from this one. Let's see what else we've got. Let's see. How do I clear all this junk? I could do it like this probably. Come on. It seems a little slow. There must be a way to just clear all. Nope. All right, well. All right, well, anyway, while I do this, I hope y'all are having a good day and all that other stuff. I guess I can do this with one hand while I search for the other problem in the other one. Let's see, so I have one circled 18. I don't know if I wanted to go to 18 just yet. I guess I really liked 18. Oh yeah, I do really like 18. Hopefully you guys can, let's see what 10 is, because I liked 10 as well. Oh yeah, here we can do 10 as an intermediate one before we get to 18. How do I just erase all? There must be a way. Oh, clear all drawings. Sweet. Okay. All right. So I'm going to look at 10 here. And 10 looks like this. Hopefully you guys are able to follow along a little bit on this is on practice 5. So here is a plate. Okay, and it's got some things going on, and it's got a point right here. This is pinned right here. I may have to run away in a second. It appears that my dog is about to start barking. We shall see. So this is point A. This is point B. There's a point right here, C, which comes up in the next part of this question. And let's see. So we've got 100 millimeters here, 0.1 meters. I'm going to go here. This is 0.2 meters. I'm converting from millimeters because, a lot of times they give it to you in a unit and you're just like, let's just go ahead and change it right now. And then this is 200 here. This is 0.2 meters. Okay, and this A is acting at an angle here of 25 degrees. Okay, I think that's it. That's all the information. Okay, so we want to determine the moment of the force about D. Oh yeah, that's right. This is where I wanted to do this. So we're going to be working around this point here, D. And so the first thing they want to know is, okay, we want to know the moment at the moment caused by A, I guess. I don't know how to notate that. So this is required. We want the, I guess this is given. We want the moment at D. Okay, so equals what? Okay, so the reason that I got this one is because basically of your question, Parker, is I wanted to think about doing this 2 different ways. Okay, so the first way to do this is to figure out a moment. You can do R cross F. Okay, and this we have to think about directions and things along those lines. So the first thing we need to do in order to do R cross F is let's figure out the R. Okay, now R is relative to the force that we're working with. Okay, so let's see, I'll do this in like green. So here's our R vector. Okay, and so R is going to go from D to somewhere on the line of the force. Okay, so I could have done R to, like I could have drawn an imaginary line to somewhere over here and done R to over there. Now that would be a lot more work than is necessary. I could have done it anywhere along this line. I could have done an R. Okay, and that would have been fine. I don't know why you would do that. That is completely unnecessary and way more work than it's worth, but you could do that. Okay, so, but sometimes you might want to do that. Okay, so just, be aware of that. Anyway, so my R vector is going from D to A. Okay, so that tells me something about the sign. So like right now, this R vector, I can tell that in the X direction, it's negative because it's going from D to A. And in the Y direction, it looks like it's also negative. Okay, so this is going to be negative in the I and negative in the J. Okay, and now I just need to give it, signs, right? Or whatever, magnitudes. So in the X direction, it's 0.1 meters. And in the Y direction, it's 0.2 meters. Okay, and I'm going to go ahead and put the meters out here because I didn't feel like writing it in there. Okay, and that's how you get your R. Okay, now to get your F, you will do, we have to deal with, our sines and cosines, which hopefully at this point are becoming normal for you. Wait, do we have a magnitude of this force? The 306 Newton force. Okay, so this is 306 Newtons. Okay, that's in my givens. Okay, so for that one, we're going to need sines and cosines, and hopefully you guys are getting pretty good with those at this point. And so I'm going to do an X direction, or the Y direction, and the Z direction, or excuse me, the X direction. Again, this is X, this is Y, and Z is coming out of the board towards your face. If we do X is my fingers, Y is my palm, then my thumb is coming out towards my face. Okay, and my fingers are going counterclockwise. So that's going to be positive Z. Okay, so anyway, so for that, we want, hopefully you guys can do the trig. So this one with that 25-degree angle, this is 306 cosine of that 25 in the I. Okay, and I've got the newtons outside, and that's a positive. I like to put the plus sign, even though it's not necessary, just to remind myself that I took care of the sign. Okay, and then we'll do plus 306 sine 25 in the Y direction. Okay, so that gets a little J. Okay, I'm going to go ahead and solve for that because it'll make my life a little bit easier as I move forward. So we'll go ahead and say, well, 306 cosine 25, 306 cosine 25 is 277, 277.33. Okay, in the I, plus 306 sine 25, 306 sine 25 is 129.32, 129.32 in the J, and that has newtons. Okay, so if we do R cross F, then what we're going to do is going to go I, J, K. And now you can do Kramer's rule as Jeff Hansen likes to do it. I actually like to do it the old-fashioned way because for a 3x3, I just don't think it's necessary to do a Kramer's rule. But here's our initial matrix, R cross F, and we'll go R, negative 0.1. I'm not going to put the units in here, 0.2, because it just gets messy in there. And then this will be 277.33 and 129.32. Okay, and it's important here to get the signs right. The signs need to be correct. And if you do that, it'll spit out the correct answer for you. And so what I'm going to do is 0.1 and negative 0.2 and 277.33 and 129.32. All right, now the nice thing in 2D is everything that has a, is that you've got these zeros in here. So much of this is going to go away that it's going to be really easy. So like that one.
I think you put K instead of J.
Oh, yes, thank you. Thank you, you're correct. Okay. I might have noticed eventually. And now it's got two arrows, okay? It's really, really directional. So like this one goes away and this one goes away because of that zero. And then we get a K right here. Okay, and that one gets a positive. So what's that? That's, well, 0.1 is easy to multiply. So I'm gonna get negative 0. Negative 12.932. Okay, and that's Newton meters, newtons times meters. Okay, and then we'll go back to, and then we'll do these other ones, and these will get negatives. So that one is the one we want right here. Okay, and we'll go, so that one becomes positive because we have to take the negative of the ones that are diagonal in the other direction. So 0.2, I can't quite do 0.2 in my head. 0.2 times 277.33 is 55.466. 55.466 newtons times meters. And then you've got a 0 and you've got a 0. Okay, so those all go away. Okay, so the moment equals this, which equals, I wonder if I can take, y'all's screen is right in my way at this point. All right, so we take that and we subtract 12.932 equals 42.534. 42.534. Okay, newtons times meters. And if you report it, I would say moment equals 42.5 Newton meters. Okay, so that would be the answer. Okay.
Sorry, not to be the person just like always harping on signs. Is that not also minus 55.466?
Okay, really good question. No, by all means. So the most confusing thing with moments is the signs. So please harp on the signs all you can. So when you do it this way, these all get multiplied by a positive 1, positive 1, positive 1. And the ones that slant backwards get multiplied by -1, -1, -1. Okay, so this was negative 0.2 times 277.33 times this -1.
Gotcha, that's just what I missed.
Okay, yeah, so it's just like when calculating the determinant. And there's a lot of different ways to calculate the determinant. For a 3 by 3, I find this to be the easiest. The Kramer's rule, which Jeff Hansen uses, is fine. I just don't, I think I get a little confused because there's just too many negative signs. To me, the negative signs are much easier if you just spread it out this way. Okay, so we're going to do this again, but I'm going to do it the other way, which is moment equals, and what I'm going to do is basically I'm going to call it the moment for, basically we have two forces, and I'm going to do force in the x direction times its perpendicular distance plus the force in the y direction. I don't really know what to call it, d perpendicular, whatever. I don't know how to write it. And then force in the y times its perpendicular distance. Okay, so this is the way I prefer to do this because this is more intuitive to me. And so here you have to plug in the right signs and it will give you the correct sign out here as long as you don't make an error. Here we're going to plug in I'm going to plug in all positives. And then I'm going to think about what the signs are. Okay, so m equals f in the x direction. Well, I know what that is right here. Okay, that's 277.33 newtons. Okay, I'm going to leave a little space here for the sign because I want to think about that. And then I'm going to do d perpendicular. Okay, so that means I'm going to take this force right here, this red force, and I'm going to kind of like extend it down until it's perpendicular to this spot. So here it is right here. Okay, so it's acting. So now I know this perpendicular distance is like this. Okay, and I'm going to write that distance right here. Okay, and that's 0.2. Okay, that's the perpendicular distance, 0.2 meters. Okay, now I have to think about which way is that causing this thing to spin. Okay, that's where my sign comes in. Okay, and so I'm going to think about having so I'm going to put my thumb right here at D. Okay, and I've got my fingers curling. Okay, and my fingers curl counterclockwise. And hopefully you can see that this force right here, this X force, is reinforcing that curl. Okay, the curl of my fingers. Okay, it's because it's reinforcing, that means this is a positive sign. Okay, you should note that somewhere down here below here, that, by the way, is this diagonal right here. Okay, 277 times negative 0.02 with a negative sign in front of it. That's that diagonal. Okay, now we're going to do Fy. Okay, now Fy we know is 129.32. So 129.32 newtons. Okay, and I'm gonna do the same thing. I'm gonna think about perpendicular distance. I'm gonna take this thing right here. It actually doesn't act where we draw it on this triangle. It actually acts right here, okay, at A. And what I'm gonna do is I'm gonna project it until the distance to D is perpendicular. So I'm gonna put it like right here. Okay, noting that this is now its perpendicular distance, which is kind of hard to see, but there's its perpendicular distance, 0.1 meters. Okay, now we have to think about which way is it causing things to spin. Okay, and so if we look up here, hopefully you can see that this thing is going counter to this spin, like it's pushing against it, right? Like if I were to, I don't know, this would cause a spin going this way, which is the opposite direction as your fingers curl around D. Okay, so that's going to be a negative sign. Okay, and note that that's this diagonal right here. Okay, we've got the negative 0.1 times 129.32. Okay, and so ultimately, like I don't even need to put this in my calculator because you can see that we're going to get the exact same answer, right? So we're going to get moment equals 42.5 newtons times meters. Okay. And a lot of times, what a lot of people will write is they'll do something like this in front here to let you know that positive is counterclockwise, and that's them basically saying I used a right-handed coordinate system. Okay, or sometimes you'll see moment equals 42.5. I think this is the way Connect does it, and you'll just kind of draw that. Okay. Questions?
I'm good.
Okay. Hopefully, and Parker, keep me honest on those signs. Like, do not feel like you have to apologize or anything. The hardest thing on moments is getting the signs. It's easily what messes everything up, especially if you get to 3D, which I think maybe we'll try 3D now. Oh no, well, we could do a dot product. Let's do a dot product because let's see, we've got 35 minutes. Let's do a dot product. Dot products are they're annoying. I forget about dot products, but it is something you're supposed to learn in this class. So it's just kind of like a throw in that doesn't show up often enough, so everybody forgets it, including me. Every time I do a dot product, I have to go, remind myself. So I'm going to clear all drawings. Okay, so I'm going to go to, if you guys are on practice 5, I'm going to go to problem 13. Does it have to be 13? It could be 13. It doesn't matter. All right, so 3 cables are attached to the top of a tower. Determine the angles formed by cables A, B, and AC given a certain height of a tower. All right, so we've got a tower here, and I'm not going to draw a tower because I'm not really good at drawing towers. It's just going to be kind of like a long obelisk thing. And then it's got so this is attached at the base at a pin connection. And then, so this one, and hopefully you guys are understanding, this is why your problems in the book always give you the coordinates. They tell you which way is X, and they tell you which way is Y. So Y keeps going up like this. And the reason they do that is because they want to make sure you're using a right-handed coordinate system. And it also, from a grading standpoint, makes it a lot easier. So this is Z, and this one up here is Y, if I can just draw that in there. Okay, and so we've got, so this thing is, well, it's 52 meters high. I'm having a hard time figuring out how to draw that in there. Let's draw this like this. And we're going to go straight up. So this is 52 meters. Okay, this distance right here is 14 meters. We got a few more cables coming off. This one's coming off to somewhere out here. That curl is disgusting. So let's do that again. Right out there. And this is to a point here, which is going to be, oh, no, we want it to be parallel. That's the only way this makes any sense. Okay, so this distance is 16 meters. This one's 12 meters. And C is out here somewhere. Okay, and it looks like, no, it's also 16 meters out there. And it's 24 meters in this direction. Okay, 24 meters. Okay, this is point C, this is point B, this is point A. Yeah, and so we want to know, well, this is point, no, this is A. Oh, this is D, okay. All right. Okay, there you go. So ugly drawing. Again, note, we've got a right-handed coordinate system. If X is my fingers, Y is my palm. Okay, so if you kind of do that kind of in your own little space, you notice that Z is your thumb. Okay, and if we were doing, what do you call it? If we were doing moments on this one, just to kind of think about it real quick, Z direction, the positive curl of your fingers would be kind of over the top. Okay, and if we were doing X, if we were doing an X direction moment, we would point our fingers, our thumb, and we would just like, okay, we've done our right-handed rule to get the directions X, Y, and Z, which one is positive. And then in the X direction, we would point our thumb to figure out the positive moments, and it would go over the top of X. So that would be a positive moment in the X direction. And in the Y direction, if I point my thumb in the positive Y direction, we would note that it's going kind of like my fingers are going kind of that direction, over the top of that. Okay, so just something to think about for the next problem. Anyway, for this one, we want to know the angle between AB and AC. AB, I really don't know how to write that. Maybe the angle between AB and AC equals what? Okay, and so this is a dot product. And the formula for the dot product, really for any two vectors, if we had a vector, I don't want to call them A and B, but let's say we have X dot Y, okay, equals the magnitude of X times the magnitude of Y times the cosine of the angle between them. Okay, so this is the easiest way to get an angle between two vectors. You could probably do a cross product here too if you wanted to. I just don't really want to do that. Okay, so let's get the vector for A, B, and AC. Okay, so AB, the vector, let's see, this is A up here. Here's B down here. So the vector is going to look like that. So it's going to go from A to B. Okay, so in the X direction, so AB equals from A to B. Let's see. So in the X direction, we're going, let me get some red here. In the X direction, we go that far. Okay, so that's going to be positive 16 meters. Okay, in the Y direction, well, we went from here straight down. So that would be minus 52 meters in the J direction. And in the K direction, okay, so that's the Z direction, we're going to go this way. So that's plus 12 meters. Okay, in the K direction. Okay, now we'll do AC. And let's see, so I'll use green for that one. Let's see, in the X direction, well, let's see, we went from here to here. Okay, so that's also 16 meters. In the Y direction, we also went down 52. Okay, this is turning out to be fairly boring. And then in the Z direction, well, we went this way. Okay, so we went negative along Z. So minus 24 meters in the K direction. Okay. And before I plug all this into this formula, let's go ahead and get the magnitudes here. So AB, the magnitude is the square root of 16 meters squared plus 52 meters squared. And again, I don't worry about signs on magnitudes because everything's getting squared. And 12 meters squared. Okay, and that's AB. This is AC, square root of 16 meters squared plus 52 meters squared plus 24 meters squared. Okay, and that's just a calculator away. In fact, I should just make up numbers rather than waste the time with this, because presumably you guys can do this. Okay, to the 0.5, okay, 55.714, 55.714 meters. And this one will be 16 squared plus 52 squared plus 24 squared raised to the half power is 59.464. 59.9464 meters. All right, so then to solve this, we're basically just going to plug all this into this formula. Okay, so the way we do an AB dot AC equals magnitude of AB times the magnitude of AC cosine theta. So the way we do A dot AB dot AC, I always love dot products, so I always think they're nice and easy to solve, is you basically multiply these two and add them to what you multiply these two by, and then add them to what you multiply these two by. So basically we get 16 squared, which is, I think it's 256. It is. So we get 256, that's meters squared. Okay. Plus, in this case, 52 squared, which I have no idea what that is. 2704 meters squared. And then we're going to add this one right here, 12 and 24. So 12 times 24 equals 288. So, excuse me, that's a minus 288 meters squared equals, now I need the magnitude of A times the magnitude of B. So that's 55.714 meters times 59.464 meters cosine theta. Okay, so so now basically I'm going to add up all of these, divide by this, and then take the inverse cosine of whatever that is. So theta equals, please let me know if you want to see this algebra. Okay, and so I've added all of these. I'm going to divide by this product, or I'm going to divide by both of those in turn, 55.714 divided by 59.464 equals 0.806. And then I'm going to take the inverse cosine of that answer. Okay, and I get 36.242 degrees. Okay, so I would report 36.2 degrees. Okay, and that's how, you know, anytime you're dealing with things and you need an angle, that's probably the easiest way to do it. Okay, any questions on that one? Again, doesn't show up. Go ahead.
I just have a question. How did you get the A and the B, the 256? How you get that?
Okay, so this 256, so when you calculate a dot product, you basically it's kind of like if you do the i's times each other,
Oh, okay, I got it.
the
I got it.
j's times each
Yes.
other, and the k's times each other.
Okay, so you multiply the AB times the AC. I see.
Essentially, yeah.
Yes,
Well,
I got it.
yeah. Technically, it's not a multiply; it's a times. And you know, if you really get into linear algebra, they'll call this, I can't remember if it's an inner product or an outer product. I can't remember which is which, but one of them, the dot product. I think the dot product is the inner product, and the cross product is the outer product. You know, so if you, but yeah, it's a special multiplying technique, right? So you just multiply the i's together, the j's together, and the k's together, and you add them. Okay.
Right. Yeah.
This has
Thank
special.
you.
This is also, I think this is called divergence in linear algebra, but I'm not really a linear algebra fan, as much as I recognize its importance. Okay. All right. Any other questions? All right. I really wanted to do 18, and I think we've got enough time for that. So let's go ahead and do 18. 18 is going to be the hardest one for me to draw. I really wish I could figure out how to annotate on the drawing itself, which I can do on the computer, but I can't do on this whatever this thing is that I'm using. Okay, so if you guys are in practice 5, I'm going to do 18. I really love this problem. It would be a great test problem, in fact, although it's challenging. Okay, so so I'm going to draw it real quick as best I'm capable. Okay, so here's the z-axis. Here's the x-axis. And here's the y-axis. Y-axis, and just kind of dotted underneath. Okay, and there's some kind of weird, you know, all the things that they draw in this course are weird, I guess. You know, they're just there to, you know, make a point or to help you figure something out, you know. Okay, and then it's kind of got a little, I don't know what you call it up here, a little. Okay, so it's like this, and then it's got, so here's kind of the x direction. And off of that direction, there's a lever going kind of out like this. Okay, and this is 35 degrees. Okay, and my dog has come here to say hello. Okay, Rocky boy, you are a good dog. Everybody loves you. Okay, I know. Go away. Okay. Yeah, and it's got a handle right here. Okay, now that handle, actually, I wouldn't ask this on a test. It's a little annoying to see what's going on here. There's a, so this is in the Y direction. This, oh yeah, this is in the Z direction, kind of this little line here. It's in the Z direction, and there's a force right here going like this. Somebody's trying to call me. They don't know that I'm doing something. Okay, and this force, that's 15 degrees, 15 degrees. Okay, I like this problem because it is hard. Okay, it's hard to visualize, and hopefully that means that if you can visualize this, you can visualize like a lot of things that go into this class. So I'm gonna call this 110 Newton force because that's what, okay, this plane right here, this 110 Newton force is in a plane parallel, a vertical plane parallel to the XY plane. Okay, and it is applied to the 220 millimeter long handle of AB. So this thing right here is 220 millimeters, excuse me. Okay, the numbers don't really matter. We could work this all in symbols. Okay, so 220, so this thing right here is 100.150 meters. Replace the force with an equivalent force couple system at the origin O of the coordinate system. So we want to replace all of that with, basically we want to figure out what's going on at O. Okay, so this is O origin. Okay, so this is given. Required is we want equivalent system at O. Okay, so required equivalent system at O. Equivalent system at O. Okay, so a little bit challenging here. So, you know, hopefully you can see that this is a little bit weird. Okay, so the first thing I want to do is I only have one force to work with here, and that's this 110. So, and we're in 3 dimensions, so, which is really annoying. By the way, this 35-degree angle, this is in a plane parallel to the XZ plane. Okay, so this is, sorry, I got a little bug stuck to my hand. Oh, that's that disgusting dog slobbered on me, sorry. Okay, so this is in a plane parallel to the XZ plane. I assume XZ plane. Okay, so, all right, so first thing I want to do is I want to think about this 110 Newton force. Okay, so I'm going to say the sum of the forces, okay, or the total force here, and there's only one force, so I don't really need to even sum it. So I can just go ahead and say this particular force, which is going to be, is basically, I've got this 110, okay, and I need to kind of, you know, break it down into its components. And it looks to me like if it's in a plane parallel to the XY plane, is that right? No, the YZ plane, excuse me, the YZ plane. This is the YZ plane. Ah, man, it's amazing how that gets stuck into your head. Okay, YZ plane. Okay, then we're gonna have a force that goes basically downwards in the Y direction. Okay, and we're going to have a force in this direction, in the z direction. Okay, so we just need to do some trig in order to get that. Okay, so let's see. So we have to do our trig. And it looks like, so 15 degrees is right here. Here's my right angle. Okay, so it looks like we've got 110 newtons. Okay, and so I'm dealing with, so this, let's see, so let's see, we want to, so let's see, in the x direction, we've got a 0. Let me go ahead and put in an x, a 0 for x. Okay, equals 0 in the x direction. Okay, in the y direction, it's going down, so I'm going to get a negative 115. Okay, and that's the opposite of this angle, so that'll be the sine of 15 degrees. Okay, in the j. And then in the z direction, it looks like it's going in the positive z direction, so plus 115, and that's the adjacent side to that angle. So it'll be cosine 15 degrees, and that's a k.
Where's 115 coming from?
Oh, 110, excuse me. Sorry, thank you. So I assume that answers that question. Okay, so that's newtons. Okay, and again, just for simplicity, I'm going to go ahead and solve this because it just makes my life a little easier to plug this in fairly early. Sine 15, so that's what, 28.470, negative 28.470, j plus 110 cosine 15. Oh, no, don't do that. 106.25. 106.25 K. Okay, and again, this is newtons. Okay, so now, okay, so basically, like when I do my equivalent system at O, okay, so here's my equivalent system. Okay, so, well, I know F equals the same, okay, equals negative 28.5 in the J plus 106 in the K, okay, newtons. Okay, that's my equivalent system at O. Okay, now we want to get the moment. Okay, so we've got the force part of it. Now we need to figure out what the moment's going to be, and there's going to be a moment in potentially all three directions. Okay, and that's why I like this one, is it makes us think about that. The easiest way to get the moment here is to do kind of like is to do r cross f, because we're in 3 dimensions. So let's go ahead and do it that way. Let's see, never used blue here. So here's my r vector. It's going to go from O up to somewhere on the line of that force. Okay, so r equals, now we have to think about x, y, and z here. We're going to have some meters out here. And let's see, in the x direction, what I need to know is I need to know kind of like this direct distance, which is hard to kind of get at, right? How far do we go in that direction? Well, easy. Well, let's start with the easy one. In the z direction, I want a 0.150. 0.150. Okay, and that's positive. Okay, so then now we're there. In the x direction, we're going to want to go basically along this line. Okay, so here's the z direction is kind of like this, I guess. Right, so now this angle, so this is in the x direction, this is in the z direction. So this is a right angle right here. Okay, and here we've got 35 degrees, and I know the hypotenuse. Okay, so in this case, the x direction is 0.22 times, it looks like that's the adjacent side, so that'll be cosine of 35. Okay, and that is in the positive x direction, because this is the positive x direction. Okay, so that'll be I. And then in the j direction, yeah, we'll need j, so which way is y? Oh, sorry, this was y, wasn't it? Okay, plus 0.15 J. Okay, so this is not the K direction. Okay, and then we need this is the Z direction right here, and it looks like that is negative because it's going in this direction. So minus 0.22, and this is the opposite side from that 35-degree angle, so we'll do sine of 35. Okay, and again, I'm just going to plug this into my calculator because it makes my life a little bit easier. 0.22 cosine 35, 0.18021, I plus 0.15 and the J minus 0.22 sine 35 equals 0.12619 K. Oh, there should have been K right there. Meters. Okay, so if you want to do the moments for all of this, all at once, the way to do this is R cross F. This is nice because it takes care of all the signs for us. And so that's kind of a nice thing about it. So if I want the moment from this force, doesn't even have a name, moment from 110 at O. Okay. The nice thing about this is this is going to create, it's going to take care of all the signs for us and all the directions. So we'll do I, J, K, I, J. Okay. So, okay. And like I said, I like to do it this way. You can use the Cramer's rule if you want, but you know, that's entirely up to you. Let's erase that because I don't know. Okay, so here we go. So R goes first, 0.18021, 0.115, and negative 0.12619, 0.18021, 0.15. And unfortunately, in this case, we don't have any zeros. So that's really frustrating. Luckily, on the force, we do have some zeros, so that'll help us. So in the I direction, we get 0 and 0, so that will make our lives a little bit easier. In the J, we'll get negative 28.470 and 106.25 and negative 28.470. Okay, so I'm just gonna kind of do the work down here. I can't move this screen, which is super annoying. Oh yeah, I can. Okay, good. Okay, we don't need those lines. All right, so let's see. We'll do this one. Positive. Let's see, 0.15 times 106.25 equals, let's see, 15.938. Okay, and that's got an I. Okay, here's the J. That's got a 0. I didn't quite get there. Here's a K. Okay, minus, let's see, 23.470 times 0.18021. We get minus 4.2295, and that's got a K. Okay, and now we'll go the other direction. And let's see, so this one is a 0. This one is going to have a negative sign, minus 0.12619 times 28.470. Okay, minus 3.5926, 3.5926 I. And then here's my J, which is going to have, looks like it's going to have a negative sign. Okay, because we've got positive times positive, and then because it's a back diagonal, it gets a negative. Okay, so 0.18021 times 106.25 equals 19.147. 147 J. Okay, so our final answer here is, let's see, we group terms, these two go together, 15.938 minus 3.5926 equals 12.345 in the I. So the moment equals, the J is negative 19.147 in the J, and the K is minus 4.2295 in the K. Okay, so that means over here, for my final moment, I could write 12.3, this is newtons times meters. This is kind of sloppy work. I usually like to keep my units all the way, but this whiteboard's pretty small. I minus 19.1 in the J, minus 4.23 in the K. Okay, and that's newtons times meters. Okay. So that's the answer, more or less, assuming I didn't make an error, which is always very possible in these. And, you know, obviously don't beat yourself up if you make a little error here or there. These things happen. This is, you know, there's kind of a lot of little tedious calculations going on here. If you have time, it's good to punch things into your calculator twice and afterwards make a little note to yourself to check your signs. I will note that what these things mean is that, like, if I think about this moment right here, this positive I moment, okay, I'm going to think about my thumb going in this direction, thumb. And that means that this 110 Newton force is causing this thing to want to curl in the direction of my fingers. So my fingers are going to kind of curl over the top of that thing, if that's my thumb of my right hand. Okay. And sure enough, like, it seems to make sense that this 110 Newtons would make this thing want to curl, this frame to curl over the top of that thing. Okay. And that's why we have a positive sign right here. Okay. If I think about this 19 in the J direction, well, I need to think about if I put my thumb in that direction of my right hand. Okay, you think about, well, what direction is this thing curling? Or my fingers curling? Well, my fingers are curling this direction. Okay, and notice that this 110, it seems like it would be pushing, it would be causing this thing to want to spin the opposite direction as that. So sure enough, we have a negative sign right here. Okay, and then for the Z direction, okay, again, I'm going to put my thumb in my right hand in the Z direction and want to think about which way my fingers are going. Okay, and they're kind of going over the top here. Okay, and I think hopefully you can see that this thing, if I'm pushing out in that direction, it's kind of going to want to make this thing curl the opposite directions, and I want to make this whole thing curl that way. So it's going to go in the opposite direction. So hence we have this negative sign. Okay, so that's the idea behind this, and that's how I recommend you solve this one, with the R cross F, because we're in 3 dimensions and it'll take care of all the signs for you. Okay, now if we wanted to do it the other way, and I don't really have a lot of time here, but I'm going to try to do it the other way real quick. But I'm going to have to erase all this in a second. Do I have any questions on this way? Okay, so I'm going to go ahead and erase this. I'm going to do it the other way, which for this problem, I don't really recommend you do it the other way, this other way, but it's good if you can see it. Okay, so now we've already got our position vector and we've got our force vector. So that's good. Now erasing this thing is a real pain. Okay, but I really don't want to erase everything. Well, I kind of wish I could save that too, but oh well. You'll see that all the same numbers get multiplied if we do it this way. Okay, and so we're going to think about this as 2 forces. I've got 2 forces. I've got this force and I've got this force. Okay, I'm going to get the moments of each of those forces. Okay, so all right, let's see. So moment of the force in the x direction. So moment of force in the x direction. Okay, moment, force in the x direction at 0. Okay, equals. Okay, so that's this force right here. Okay, maybe I could draw that in a more obnoxious color or something. Okay, and I need to think about the directions that this thing is going to cause this thing to want to spin. And that's why I like to think about these things. Okay, and so one of the things is it is not going to create a Z moment. And the reason for that is, wait, hold on. No, sorry, there's no x direction force. Moment of force in the direction is that's the z direction force. Nope, sorry, that's, okay, sorry. I'm getting all mixed up here. Okay, we're gonna start with the force in the y direction. Force in the y direction around 0.0. Okay, so the force in the y direction, that's this vertical force. Okay, so we'll start with the vertical force. Okay, one thing to note is that if you're in the vertical direction, you're not going to cause anything, you're not going to cause any of this rotation. Okay, so you're not going to cause rotation in the direction of your force. Okay, that is automatically a 0. So we need to think about what is this going to do in in the x direction and in the z direction. Okay, and so in the x direction, okay, it looks like, if you think about it, it's going to cause this thing, if I had it go down here and I put the force like this, okay, so that now I'm like somewhere down in the z, y, x plane. Okay, so that this force is going to cause, first of all, it's going to be the opposite of the direction of this thing, right? So in the x direction, it's going to create a negative moment. Okay, now we need to figure out what that distance is. Okay, so we've got a force, which is, again, I'm just going to put in signs, positive numbers, and I'm going to think about the signs. Because this is newtons. And then I'm going to put in, let's see, so what's the distance? Well, it's going to be this perpendicular distance to get out here. Okay, or really, I guess, to get to here. Okay. Now, the nice thing is, in this case, that is the distance in the z direction. We've already calculated that. That's this guy right here, or girl. Okay, let's, so 0.12619 meters. Okay, and that is the moment in the x direction. So that's going to be I from that force. Okay, now then we have to ask our question self, okay, so this is in the y direction, does it do anything in the z direction? And it seems like it might, right? So if I take this force and I, so it's right here is where it's actually acting, okay, and I drop it down here. Well, what's it doing in the z direction? Well, if we think about it, it looks like it's causing this thing to spin relative to the z axis, opposite. So we're going to have a negative sign. Okay, 28.470 newtons. Okay, and we need to think about what is its perpendicular distance from that axis. Okay, so so here's where it acts. What is that distance? Okay, and again, I don't recommend you solve this. I don't recommend you do it this way on a test because this is very confusing, but it's very good if you can see this. Okay, and so that distance, notice, is in the x direction. So we've already calculated that. It's right here. So I'm going to go 0.18021 meters. And so that is the moment in the z direction. So that's going to be k. Okay. And so then we can also do the moment of the force in, so this other force, which is in the z direction, about 0.0. Okay, and again, I'm just going to do the forces, and then I'm going to do the signs. Okay, and I think we're only going to have 2 directions on this one. I don't exactly remember, but one thing we know is that we won't have a k, so we'll probably have an I and a j. Okay, because in the direction your force is in, you will never have a moment in that direction. Okay, so in the z direction, that's this force right here. Okay, again, let's get a more obnoxious color. Yellow is not obnoxious enough. Let's go with green. Okay. And so we know the magnitude of this force is 106.25, 106.25. And now, okay, so in this direction, so we want to think about what it's doing around the x-axis. So this x-axis right here. Okay. And it looks like this is going to cause things to spin that way. Okay, so it's going to have a positive sign in the x direction. And I need to think about what is its perpendicular distance. So if I kind of like extend this thing over here, its perpendicular distance to the x-axis is straight down. Okay, I can look at the picture and get that, or I can note that we've already got that. So that's in the y direction, and that's 0.15, 0.15 meters. Okay, now we have to get this j hat. Okay, and to get that one, we want to go in the, let's see. So now we're going this way. So here's my y-axis. Okay, and that's spinning, that's positive is going kind of over the top here. And so it looks like this thing is going to want to cause that to spin the opposite direction. So we're going to do a little negative sign here. And then we just need to figure out the distance, okay? And that is this distance going out here. Okay, if we extend this force out, and again, we know that distance, and that distance is this one right here. So 0.18021. Okay. And that ultimately, and we would add both of these up to get the net effect. So these I terms would go together, and this K term would stand alone, and the J term would stand alone. And I think if you look at what we just did, you should see the exact same numbers being multiplied with the last one where we did R cross F. Okay. Again, I don't recommend this method. It's for 3D. It's too hard to think about, but I mean, it's really hard to like make sure that you get it all right. But you should, if you do that, you'll add up and get all the same answers. So I've gone a little bit over, but hopefully this was helpful to you guys. Any questions on this one?
No, I don't have.
Okay. I mean, I know this is a really kind of a confusing way to do this one. So, oh, sorry, Ra, you asked which problem is that? Sorry about that. Hopefully somebody else answered. Okay, thank you, Mohammed. So yeah, so that's how you do this, you know, that method. Hopefully what I was trying to get you to do is just kind of see, you know, where all these numbers come from, what you're doing when you're cross product. The cross product just takes care of a lot of mess for you. But in 2D, I don't recommend using the cross product or doing the R cross F. I recommend doing the M times the perpendicular distance. But in 3D, I recommend doing R cross F. So hopefully that'll kind of answer your question, Parker, when you were like, well, you know, why did you not worry about the signs here, or, you know, or whatever. So yeah. Anyway, any other questions? Okay, well then I think we're out of time. If you guys have any questions that you want me to work, please feel free to email me a question beforehand. Next class we'll work on reactions. So there will be some moments, there'll be moments in there because there has to be moments when getting reactions. But unless there's a specific question about something here, I'm going to move on. Okay, so hopefully we can do this in a way that will be useful for you guys. And if you prefer, if some of you guys are like, hey, I'd prefer you to work, you know, the homework before we turn it in, we can make this a homework session and I can just work the homework problems. That's totally fine. For some people that may not be helpful though, because maybe you want to kind of fight the homework a little bit so you know where you're stuck. But you know, the point of the homework is not to give you a grade and punish you. It's just so you get a little practice. So if me working it helps you, then great. You know, so whatever you want to do. Okay, so hopefully this was helpful. If you have any comments or anything, or if you're like, you know, it would really be helpful if you did this or that, just send me an email. Okay. And
Thank you, appreciate that.
Thank you.
you're welcome. And I'll try to post a recording of this if I can make that work. Okay. Thanks, guys.
Thank you. Have a good day, guys.
Y'all too.
Yep. See you later.
Later.